Hello, so I am starting with an overview of the draw task or the graphic system for Expedition Engine. So if we go ahead and go into the task graph, we go into the tasks and we look at the draw frame task. Inside of the draw framework, you can see the first thing that happens is the draw frame is called. And that sends to the scene manager, and it tells the current scene to execute its draw. So that's the null strategy, which would have been used in the case that there was a time when the scene didn't actually need to be drawn. But if we look into the graphics scene,
Come here.
Sweetheart. If we look in the graphic scene right over here, we look in the draw strategy. In the draw graphic scene, it calls the draw to the current scene. And then that draw is called. So this draw, for every shader, it renders all of the shaders inside of the list. So it has a list of shaders that it needs to render, and then it sets, if there's something to render in that list, it sets the shader to context only once and then renders everything inside of that list. Then not in the draw task, but if we go back to the task graph and we look at the resolve frame task, this is where you call swap chain and prepare to draw. These are here so they can happen while synchronized threads is happening. And they also happen here because swap chain forces the GPU and CPU to synchronize, which can sometimes cause stalling of the CPU. So by putting it in resolve frame, it allows you to move on to synchronized threads while waiting for the GPU to complete its draw tasks. So the way that graphics objects are registered and deregistered for draw are through these functions start drawing and stop drawing. Start drawing obviously starts drawing all instances of the graphics object, and stops drawing those instances upon the next frame. The way that we keep this thread safe, because the user interacts with these functions by calling them on the graphics object, is that they register themselves to a command list. This command list is in the graphics scene. So that command, the start and stop drawing command, will be inserted into this post queue. And that queue will be executed here in the resolve frame before the resolve task work is done. It will process the current scene commands. And so that will call on the graphics manager, will call process current scene commands, which will intuitively process the current scene commands, which goes to the command list and executes all of these. So the specific start and stop drawing commands, if we look in the graphics objects, oh wait, nope, it is not in here. We look inside the commands here. We see we have an action and a graphics object to initialize, and when it executes that specific action, and the different actions that we have are registration, deregistration. So when you register a graphics object, which this would happen during the resolve frame, is it adds itself to a render list of its shader. So it knows what its shader is, and it pushes itself onto the render list. So the next time the whole frame is drawn, it will be rendered. And this can be thread safe because while in the resolve, this is all executed, so the program is neither updating nor drawing, so it's not touching the data, it's just adding things to the list. A same method is used with the particle system, where you start and stop emitting the particle emitter. You tell it to start emitting or stop emitting, and that during the resolve frame, the particle emitter gets registered to have draw called on it during the draw task. The Expedition engine uses a variety of managers for graphic asset management. Each of these managers, the user can load models into inside of the load resource function call in the load resource file under engine resources. The user defines what the names of the resources they plan to use in a variety of different settings classes. So for example, in the shader settings file, there are 6 different shaders, and if the user creates their own shaders, they can add more. In the model settings, they have the 6 different model classes which the user can use, and they also must set the number of assets they plan to have for each type of asset, and this allows all of our managers to be array-based instead of list-based, which allows for constant time access when they get the resources. So if we look in the model manager, the get goes to a private get, and the private get is just an array access using the enum of the model key, and that's how all of the assets work, is using an array. One of the settings that users can manipulate in the Expedition engine resources folder is layer settings. Here they can set as many layers as they want, the top layer being the closest to the screen, with the bottom layer being the farthest away from the screen. This is demoed inside of a very simple sprite switcher I have in our second scene of the engine, which just shows dynamically on a key press, sprites are switched from the back layer to the front layer, and you can see them move in front of other sprites on the screen. This can be used for as many layers as the user wants, or as few as the user wants. In this case, it's just 2 layers, but the user can create as many layers as they want for their sprites. The way that graphics object sprite implement this layering method is when you call set layer on a certain sprite, you pass in the enum, which sets all the instances, or if you want only one instance, to that certain layer. So you set its sprite data to that specific layer, which sets the layer to that, and then when you update the world matrix, the Z component of the position is set to the layer. So sprites with enums that are a lower number or that are closer to the top of the layer parameters are set closer in the Z buffer and are therefore in front of layers, in front of sprites, and in a closer layer than sprites that are farther away in the Z buffer or in a lower layer. And then to ensure with that layering method that the camera has the correct Z depth within its clip plane to allow for that number of layers, when we create the orthogonal camera for each scene, we set its near distance to 0 and its far distance to the number of necessary layers. So then those map from 0 to however many layers the user needs within their Z buffer. An essential part of the graphics objects and what makes them thread safe are all of the materials that the user can touch during the update thread are protected through a double buffer. That means if we look at this double buffer class, it has one matrix for the update buffer and one matrix for the draw buffer. So all of the graphics object classes use these double buffers for any piece of data that the user can update. So the user can update the graphics object's world matrix. If we look in the graphics object color matrix, you can update the colors. So we have an array of double buffers for the mesh colors. And so while that is used to store data on the side of the CPU and to make sure that the update thread and the draw thread not only sync up, but sync up in a thread safe way. In order to send the minimal amount of data to the GPU, I also have data buffers which format the data in the way that the GPU is expecting to read it and the way my shaders expect for the data to come in. So if we look back in our graphics object, when we go to render, we put all of the color matrices into our data structure from the double buffer. So this is a double buffer, and this is the GPU data structure. So because we use those double buffers, that means the double buffers that we have is we use the matrix double buffer, we have a vector double buffer, and we also have a pointer double buffer. So that means that any floats or integers that needed to be synchronized in between the draw and update thread could not be passed simply as an integer. They had to be either cast through a pointer or sent through in a vector or matrix. The only case where I actually had to do that was in the case of my light manager. In the light manager, integers such as the specular or the spot exponent or the range were passed through in the z value of vectors where we knew what the z value was already going to be. So if we look into light management and we look in the spotlight, you can see here that when the user sets the parameters, they set the update because the user is always updating, only ever touches the update thread. The draw thread is completely abstracted from the user, so they have no access to that thread. So when they set the parameters, they set the position update and then they set the attenuation, but the Z component is the range. And then here you see the direction. The Z component is the spot exponent. And that allows us to minimize the number of buffers we're synchronizing, because adding a whole nother buffer adds more time because this Z value is being synchronized anyway, either way, even if it's a 0 or if it's a range. So that's passed through. And additionally, we also use that same structure to pass the minimal amount of data to the GPU. So if we look inside of the shaders, you can see here that the specular, the W holds the specular power, but additionally, attenuation holds the range, and direction holds the spot exponent. So the particle system in the Expedition engine is probably my favorite system that I made. Not because it's an amazing particle system per se, because it's not, but it really shows off what our engine can do, and plus it looks pretty cool. It adds a little flair to our engine. So I'm going to start off by showing you a couple demos, and then I'll go into how it works and how it really shows how load balancing can create major improvements inside of our multi-threaded system. So let's start with this demo. So there you can see all the different bouncing balls are shooting particles, and those particles are 2D sprites that are billboarding towards the screen. So if you give me a second, as I rotate around, you can see that the sprites, while they are 2D, they all billboard towards the camera, no matter where you are in relation to them. And then if I go over to the second scene, you can see these tanks. These really show off as 3D models, they really show off the billboarding effect as they all turn towards you. And then this is one of Sarah Asmussen's buttons right here. And if you click it, it'll switch all the tanks to texture tanks, or to color tanks instead of texture tanks. So this is a transparent fire particle texture on the tanks right now. And when you click this button, it switches over to a solid violet color tank. So the reason I like the particle system so much is all the computation is done on the CPU, but it's all done entirely on the draw thread, and it's done without any explicit double buffers as thread protection. The thread protection is built into the architecture using a command list, as well as the interaction between when the user updates information and when the draw receives that information, and it keeps it completely thread safe, which I find very interesting. So if we look, if we start by looking into the particle emitter, this is what the user interacts with. The user can create particle emitters. They can set the position, they can set the color, they can set the texture, and they can get those back. And then they call register and deregister from scene in order to have it start emitting and stop emitting. They also can set it to either a texture, as we saw in the demo, or they can set it to a color light. In the future, I'd also like to add texture light and color without light, but this is that right now. If we look into the particle emitter and register to scene, it sends a command to the graphics scene manager, and this is the same command list that we saw graphics objects registering themselves into in order to start being drawn. And it's the same for deregister to scene. It goes to the beginning, and at the top of the next frame, the graphics scene manager executes that command list, and it will start rendering it. So what happens when this starts rendering is it triggers next burst. And what triggers next burst does is the particle emitter manages alarms for every burst, as well as for itself, so it knows when to make the next burst. This is the biggest easy optimization that could be made for the particle emitter. Is currently it uses our alarm system, which Sarah made. However, it knows more information about itself than the alarm system can, so it could manage these more efficiently by putting them in an array, and not the current alarm system has to be managed as a multi-map, so it has access to the alarm component as well as the time, but the particle emitter could abstract more of that away because it knows more about itself than the alarm system could. So that would be a great optimization, because this alarm system, using it so frequently for every single particle, is incredibly costly. So trigger next burst always happens on the update thread, and so what that does is it just creates the next burst and it sets all the alarms. If we go and look inside of the alarms that it's using, we have the next burst alarm. So when it's time, it has a pointer to the particle emitter, and on alarm, it just triggers the next burst again. And then we can also look at every single burst has an alarm for its lifetime. So these are the alarm for burst lifetime, and it has a pointer to its particular burst, and then it just stops drawing the burst when its lifetime is up. So instead of having the actual classes called burst, the graphics object particle, it's in here. The graphics object particle basically functions as a burst because every burst is hardware instance, so only one draw happens per burst. So if we look in the graphics object color, it just holds all of its instances and it knows when, and it starts drawing, but it never has to call stop drawing on itself because that is the alarm's job. Click on this. And so this is also the reason that this is entirely thread safe without any double buffers is start drawing is called by the user on the update thread, and it accesses information on the particle emitter that's also set by the user on the update thread. So accessing this information can never be a conflict. And so since all the information is set and accessed on the same thread and then used on the other thread, but the using on the other thread is just accessing this copy of the data, and this data is never being set. This data is always being set before the draw occurs. You see that all the data accessing to the update thread is happening before you start drawing. In the render, it's just using information that it already has access to internally that's not being touched by the user dynamically. So in that way, the architecture allows it to be thread safe without using double buffers, because the user sets all the information on the update thread, and then there's a command, then it enters into a command queue to start drawing, and then everything happens on the draw thread with no interference from the user. In order for the user to mess with the settings, it has to wait till it stops drawing, and then when it starts drawing again, it will get the update the user applied. So during the actual cycle of the burst and during the draw call, the user can't touch any of the information. This update positions call inside of the particle base is the one in charge for billboarding the sprites or the models towards the camera. So for every instance that it holds, it gets the direction towards the camera, which will become its front axis. It computes the right axis using the direction towards the camera and then pulling it towards the global up, the up in the Y direction, and then it computes the actual up axis using the right axis found in the direction to the camera. This ensures that the models aren't flipping funny ways, and that they're always facing in the way you would generally expect them to face. It makes sure it's normalized and the W's are zeroed out, and then it sets the world data and computes the world inverse. The final major aspect of my graphic system is the hardware instancing component. So if we look here in all my shader objects, in the layout description, I now have other buffers that aren't just for the vertex data. I am now adding input data per an instance. So you can see here, up here's my vertex data, and down here I have two separate buffers indicated by the fourth parameter, one for the world data and then another for the material data. So that is sent to the GPU per an instance if we look in the graphics objects. So this is shader color light. If we go to the graphics object and go to graphics color light, we can see in here it holds a buffer for the instance data, and it has one for the world data. Like I showed you, there's one buffer for the world data and then the next for the material data. So if I look in here, when it renders this, for every mesh, it copies the instance data over to a resource into the instance buffer, and then it copies both of them, and then it calls, and that sends that to the model to set to context. So now when we set the model to context, we're not just setting the buffer data to context, we're also setting this instant data context. So the vertex buffer no longer just has the vertex data, it also has the two different instance data buffers. So it has the first one for the world information, the second one for the matrix information. And then down here, when you render the mesh, instead of calling draw indexed, you now call draw indexed instanced, which draws multiple instances, this number of instances to be precise. Yep, and those were the major changes that needed to be made in order to do hardware instancing. There are a few issues with this. So for example, if you try to render over 1 million or somewhere around there instances of something, the buffer will become too large and the GPU will disconnect itself. There's no good way to set an assert for this or anything because it depends on people's GPU and how much your GPU is processing at the time. So that can really depend. And then if we go over to the spreadsheet for the hardware instancing data, one test I did was not instance, so only one instance per call using the draw index instance call, so using this call right here. And then I also did non-instancing using just the draw index call, so that's not using the instance call at all, but just using the index call. And I found that there's no significant difference at all in between using these two calls for your data. So even when I had 20 balls on the screen and I was drawing all 20 of them with the instance call and then with the index call, there was no significant difference in either of these. And then same down here, if we look at when I had 50 balls on screen, draw indexed was only 0.00002 faster than draw indexed and instanced. So because of that, in my system, I always use draw instanced because it creates less overhead on the CPU and there's no noticeable difference on the GPU at all. And then as you can see here, when I did tests with 50 and 200 balls comparing instanced with non-instanced, so making a call for every object versus only making one call, there was significant improvement. In between 50 and 200 balls, so that's 4 times as many balls, there was no real difference in the instance. You can see here the average was 0.000692 for 50 balls and then 0.000679. It was actually 0.0000015 faster to draw 200 balls, so there was no significant difference in that at all. Yeah, so hardware instancing is pretty cool, huh? And finally, for a conclusion with an overview of the general data, we ran a bunch of tests with different balls with particles, and this was just to prove that our system is the best when you are doing load balancing. So since particles run entirely on the draw thread, and then the collision and the updating the position for the balls and the mock physics we have runs entirely on the update thread, when you had the correct amount of both balls and particles, there was a real load balance where the update and draw were very similar, and this would cause the most improvement. So if we look over here, so if we look over here, we get more improvements, and then the improvements start to die off. If we come over here and look at this, where they max out, where the improvements are the greatest at this multi-threading being almost 100% faster than the single-threaded, is where the draw and the update are the most even. So up here, draw is significantly more than update. We still get improvements, but they're significantly less. And then here, they start evening out, draw still being more. And then as they get closer in value, our improvements only increase. And then they max out here at 40 balls where they are the closest. And then they start separating again, the draw and the update. And our improvements start decreasing. So it's all about in our engine finding that perfect place for your specific scenario where your draw and update threads can be the most balanced. And that's where you will find the most improvements over single-threaded.